Okay, so uh, so we were looking at codecs and coding decoding. So we talked about certain basics of error correction. Today I am going to cover three important general techniques of decoding, and after that I'll give you a couple of examples. For example, the first codec, which is Hamming code, which is quite popular to correct single bit flip. So I'm going to give you the construction for that code. And then we are going to cover certain cyclic one and then BCH, and then I think that will be enough for you to have certain basic things in codecs. So as you know, code is nothing but a linear code is nothing but k-dimensional subspace of, I am talking about only binary code, and C is denoted by N, K, D. N is the length, K is the dimension of the space, and D is the minimum Hamming distance. Now, for encoding, there are two ways, as I mentioned. One is generator matrix, and other one is parity check matrix, right? So if there are k bits, you multiply with the generator matrix, which is k by n, and you get n bits. That is one way of encoding. Another way of encoding is that because the subspace can be described by either generator matrix or the parity check matrix. So then you can use the parity check matrix for the code to construct the whole encoding procedure. Okay. So in case of parity check matrix, we take k bits, we add extra n minus k bits such that hx transpose is equal to 0. This x is a whole vector. So now, in order to decode, if you recall the classical example of repetition code, C is equal to 0, 0, 0 and 1, 1, 1, that is space, which is a one-dimensional space. And how do we decode? If we send something either 0, 0, 0 or 1, 1, 1, and suppose one bit is flipped, so how we used to decode? We just compare received vector, compare with both the one from which it would have sent, right? One could have sent it. And then you compare in terms of distance, the Hamming distance, whichever is closest, and then you decode like that, right? So this is kind of bit lengthy procedure if the code size is quite high and so on, right? So then it's very difficult. I mean, it's a lengthy procedure. So there are certain observations which help you to decode it in a much better way. So first of all, I am going to tell you what is known as sphere decoding. So what we do, we take the space C, take a vector x in C, and we draw a sphere of radius t along x. What is t? T is greatest integer d minus 1 by 2. Okay. So this is all those vectors y in Z2n such that distance between x comma y is less than or equal to t. Right. So we draw these spheres. So we take a vector x in C, we draw a sphere of radius t where t is greatest integer d minus 1 by 2. And so what is the definition of the sphere? All those vectors y in Z2n such that the distance between x comma y cannot exceed t. Now you see, this means if the code has distance d, it has error correcting capability t error bits. Because if there are t bits flipped, it will fall into one of the sphere, right? I mean, so essentially, certain properties are there. First of all, these spheres are disjoint. Okay, for all x and y. See, obviously x is not equal to y. When we take two distinct vectors x and y in C, draw these spheres of radius t, they will be disjoint. Okay, this is first property. Second property, if you take union of all these spheres, it will be sort of it will, of course it will be be sub, so means all these vectors. So basically what is happening, whole space we are partitioning into spheres. Each sphere has certain vectors from the space, right? And some vectors will be outside of the spheres as well. So basically I can draw a picture here. So if this is the whole space, we draw, and maybe this is your C. We draw a sphere X here. I mean, at X we draw a sphere, at Y we draw a sphere. So these spheres are disjoint, right? And so the distance between, so the size of this sphere is T. I mean, the radius is T. Right? So these kind of spheres are there along each code word X, right? Now, this X contains, of course, apart from C, it also contains vectors from the whole space, right? I think the picture is a little bit incorrect, but it will have some vectors from the space as well, right? So now the question is, if some vector, because we know that normally when we want to send some vector, I am sending it from the C. If I send X from C and we receive Y with T errors, it will fall into one of these spheres only. Right? So I will just check which sphere it is and look at the center of the sphere and say that this is the actual vector that was sent. This is known as sphere decoding. Got it? Any question at this point? Sphere decoding is clear? Yeah. So these are non-overlapping. So each sphere is disjoint. That's why we are able to decode them nicely. C, I mean, so obviously some vectors from C will be there, but then there will be other vectors outside C, because I am looking at, so how spheres are formed. Taking a code word in C and looking at all those vectors in the space which are distance at most T from that vector X. So yeah, no problem. No, so two spheres will never intersect. That's a property that you can prove it. Okay, so two spheres will be disjoint. That's the first property. The first property. Is it coming? So, okay, so this is something. So let me take an example. Suppose C is equal to 0, 0, 0, 1, 1, 1. Okay. So what is D? D here is 3. So T is D minus 1 by 2, which is 1. Right? Now, if I take X to be, so if I take S1 of 0, 0, 0, what are the vectors that we are going to get? So of course, N is 3 here. So our whole space is Z2, 3. So basically, yeah, of course. So basically, no. So sometime it may have the whole thing also, right? So I am saying that, yeah, so intersection, that property remains true. So if you verify that, why that, in fact, why these two will have nothing common. These two spheres will have nothing common, because what happens, so suppose there is something common. Suppose there is something common. So what will happen? Suppose z vector is there, which is in both the spheres. So the distance between x comma z will be less than or equal to t, and the distance between y comma z will also be less than or equal to t, right? Right. So the code. So if code has t error correcting capability, the distance of the code should be distance between any 2 points in C is at least 2t plus 1. Okay. So if that, so that is the reason actually, you see, right? Because what happens, if it all boils down to the distance is playing a very important role. D is playing a very important role, right? So, so here actually we will have 0, 0, 0, and 1, 0, 0, 0, 1, 0. This is the sphere, and with 1, 1, 1. So you can see that all 8, in fact, in this case, this code has a special property. We call such code as perfect code. Because what happens here, the spheres, of course, they are disjoint. You can see that they are disjoint spheres, but their whole union is the whole space. All vectors are there, all 8 vectors, right? 4 plus 4, 8 vectors. Z23 has 8 vectors. So actually, this sphere is making a complete partition of the whole space, right? In general, this may not be true that the union will be exactly the whole space. Okay, it will be subset of the whole space, right? Some vectors might be there in the whole space, right? So this is the sphere. So basically, if suppose this vector x is this vector 1, 1, 0, or say x equal to not this. So code is we need to send something from this vector. This x is either 0, 0, 0 or 1, 1, 1. So if x is 1, 1, 1, and suppose one bit is flipped, suppose you received vector is 1, 0, 1, it should fall into this sphere. So we just decode that the actual vector was sent was 1, 1, 1, right? This is how we do the decoding. So this is the sphere decoding, right? Now, yes. What? So basically what happens, what is happening? We are sending a vector x from C, correct? It cannot happen because because vector whatever we are sending is sending from C only. And the center of each sphere is the element of C. Okay? That will be always the, center will be one vector is from C only. We are taking one vector from C and drawing the sphere of radius T. Actually, what is happening, because since we are sending vectors from C, if T bits are flipped, it cannot escape outside the sphere, right? So if Y is received, it has to fall in one of the spheres only. Even if the whole space does not cover, the sphere union does not cover the whole space, right? It's still, if error happens, T bits are flipped, it will fall into one of the sphere only, right? It cannot escape the sphere. And whichever sphere you see it is, you look at the center, that is a vector that was sent, right? Okay, so this is the basic technique of sphere decoding. Now, again, this method requires making spheres and so on and so forth. So by the way, I should just tell you as a tea time problem, this is a perfect code. Can you find, in fact, right now I'm asking something which is already known. I may ask a couple of things which are not known also. For example, here, there are 2 more codes which are perfect. So only total 3 codes are there which are perfect. Means when you draw the spheres around the x, if distance is d, and if you draw the spheres of radius t, which is d minus 1 by 2, actually their union is exactly the whole space, just like this. There are 2 more cases which are there. So one is this. This is known as repetition code. Another one is known as Hamming code, and third one is known as Gole code. I'm going to talk about that. So I will call them. Yeah, I mean even in general also. So basically, problem comes with our DNA storage. What happens? In the DNA storage, the distance that we use is not Hamming distance, but rather we use edit distance. What is edit distance? If x is a vector, y is a, x is a vector and y is a vector, so how distance is computed? So the minimum number of insertion, deletion or substitution required to change vector x to vector y. Now when we do this edit distance business, these spheres are no longer disjoint. They have something in common. So how do you develop the decoding procedure? That's the challenging thing. Okay, much more complicated. And that's why DNA storage, you have different kind of challenges, right? This is an easy thing because their errors are insertion of a ACGT, deletion of ACGT, or flip. A could become T, T could become C, C could become T, G, or whatever, right? That substitution error we call it. So minimum number of insertion, deletion, or substitution required to change one string to the other string is known as edit distance. A very nice, actually it's very difficult to compute edit distance between two vectors. Suppose I ask you to compute what is the edit distance between Saturday and Sunday. Saturday is one string, Sunday is another string. What is the edit distance between Saturday and Sunday? So you need to find out minimum number of insertion, deletion, or substitution required to change Saturday to Sunday. And it turns out, actually it's a dynamic programming algorithm. I don't know whether you know about dynamic programming. How do you compute? You can fill a table and compute these things, right? So, but there is not very good algorithm which is available. So if you have to compute edit distance for larger problems, many challenges are there. Actually, DNA storage, tremendous challenges are there. I will talk about some of these things. For example, if you want to store 1 terabyte of file, 1 terabyte corresponds to 1 billion fragments of ACGT, each of size roughly 300 bits. So ACGT. So, your file is converted into so many fragmented things, and then so you require reconstruction algorithms, right? All kind of things, error correction, protection, everything. So it's a bit more complicated, right? More challenging thing is there, right? So of course, and the algorithm should be efficient, the time complexity should be less and so on and so forth, right? If you really want to make this technology available for everyone, right? So that is something interesting. I will talk about more about those kind of challenges later on. So this is all about sphere decoding. Now the second thing that is important that I'm going to talk about is what is known as array decoding. Now I am taking the subspace C and I will form an coset. It is known as coset. So how do we form a coset? Take the vector C. For example, here C is what? 0, 0, 0, 1, 1, 1. And if I take vector say 1, 0, 0, add to every element in C, what you will get? You can just see here. Right. So X plus C. So I will is the coset. This is what is the coset. Okay. Normal coset definition. So now if I take X to be 1, 0, 0 plus C, what it will be? 1, 0, 0 and 0, 1, 1, right? If I take 0, 1, 0 plus C, what you will get? 0, 1, 0 and 1, 0, 1, right? If I take 0, 0, 1 plus C, what you are getting? 0, 0, 1 and 1, 1, 0, right? So now you see whole space is divided into cosets now. Can you see the coset division? All 8 vectors are there, right? So whole space can be divided into the form of this coset. So these cosets are also useful for decoding. So when we send something from C, suppose we sent 1, 1, 1, bit is flipped and we received 1, 1, 0, it will fall into one of the cosets, right? So if 1, 1, 0 is received, we know that it is in this coset. So that means our actual vector that was sent was, you just subtract this 0, 0, 1 here. So you will get 1, 1, 1. So 1, 1, 1 was sent. Okay, this is known as sphere the coset decoding. Got it? Any question with coset decoding? Take the C space, form these cosets. It will be a huge array, just you need to maintain, right? And then you send X from C, Y is received, right? And it will be in one of the cosets. Here I am taking 1 bit, so this can be increased by, if there are more vectors, right? So you can take 2 bit, so for all those 2 bit flip, 3 bit flip, and so on increasing the coset size. Here, I mean, since this is 1 bit flip, everything is, it's very easy to compute, right? So this is coset decoding. Okay, X is sent, Y is received. Look at in which coset it is, and take the so this vector is known as coset leader 1 0 0 0 1 0 0 0 1, which is used to form the coset. So again, you can see that there are certain properties. These cosets are disjoint. Okay, similar like to the sphere thing, right? These cosets are disjoint, right? Okay. And of course, they do the whole decomposition of the whole space. The whole space Z2 3 is union of these cosets only, right? Disjoint union of these cosets. Very, very important property for decoding. So X is received, so X is sent, Y is received, see which coset it is, subtract the coset leader and you get the decoding done. Now I have here, distance is very, very important. Now I will show you another example where our actually distance is 2 only. And then you see what happens. Okay. Look at this example here. So generator matrix is 1 0 1 1 0 1 0 1. Our example that we took last time. State check matrix is 1 0 1 0 1 1 0 1 that you saw. So code is what? Code you can see is this, right? Lambda 1 times first generator matrix, the first row plus lambda 2 times second row, right? So this is the code over 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1 0, right? This is our C. 2-dimensional space, right? This time. The first coset is 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1 0. Then I am adding 1 0 0 0, right? And then we get second coset. Then I am adding 0 1 0 0, I am getting third coset. Then I am adding 0 0 1 0, I am getting fourth coset, and then the whole space is decomposed. Z2 raised to power 4 has 16 vectors and they are divided into 4 cosets, right? No, so the first coset is actually C itself, right? Because 0 plus C is the whole group. First coset is that one. And the coset leader, yeah, should not be part of C, right? Because otherwise you will get the same thing. That's another property. If you take a vector in C, add it to the coset, and add it to C to form the coset, you will get the whole vector, same C itself. Okay. Now, see the beauty. Now the code is having length 4, dimension 2, and distance is 2. Now distance 2 means how many errors you can correct? 2 minus 1 by 2 means how much? 0. Yeah, so then I'll show you here. Even if the distance is 2, you can do partial decoding. Sometimes you are able to correct, sometimes you are not able to correct. Okay, so let us take an example. So suppose 1111. Okay, suppose X is this. 1011 is sent. 1011 is sent. 1 bit is flipped. Okay, and you received is 1111. Right. Then what you do? You look at the coset. It is in the third coset. Subtract the coset leader. Right. And so you get the vector 1011 as the actual vector that was sent. Right. So since distance is 2, this time you are able to correct. And there are cases. So I just invite you over a cup of tea to find out the cases when you cannot correct. Okay. So choose a X and see that one bit is flipped and you are not able to correct. There is a problem because the distance is 2 only. Some cases you will be able to correct, some cases you are not able to correct. Purposefully I have taken this example so that you see that beauty also, that when you cannot correct. Okay. Now, another interesting thing. Now, so basically you understood sphere decoding, you understood array decoding, coset decoding. You just form the coset and do the decoding. Problem is that again, it takes a lot of space. You maintain the coset and so on and so forth. Can we simplify? The answer is yes. And we introduce a concept called as syndrome. Syndrome means symptoms. Symptoms of error, right? Syndrome. So what we do? Syndrome is defined as syndrome of Y. Y is a received vector. Syndrome of Y is HY transpose. H is the parity check matrix. Syndrome of Y is HY transpose. So now that means if Y is 1, 1, 1, what is the syndrome here? You can compute Y is 1, 1, 1. So H is this 1, 0, 1, 0, 1, 1, 0, 1 times 1, 1, 1, 1. Right? Compute this thing, this turns out to be 0, 1. HY transpose. Okay. Then actually you can see that I can compute syndrome of each vector in the coset has the same syndrome actually, you can see that. If the vector is in C, obviously HX transpose will be 0 by definition. So if X is in C, HY transpose is always 0, right? So okay, so first you take Y to be 0, 0, 0, 0 or 1, 0, 1, 1 or 0, 1, 0, 1 or 1, 1, 1, 0, you get 0, 0 as the syndrome. Okay. If you take the second coset, take any vector, you get the syndrome as 1, 1. Take the third row, you get syndrome as 0, 1 for each vector. Similarly, fourth row, each vector you get syndrome 1, 0. So syndrome is same thing. Now, how will you use syndrome to correct the errors? If 0, 0 is, there is no error. If syndrome is 0, there is no error. Correct. Yeah, so you just, because we know the syndrome of each coset value, right? So whenever you compute, Y is received, compute the syndrome, you don't have to maintain the array, right? You just maintain a table of syndromes, right? And see which vector coset leader you need to subtract, right? Directly. It will save the space for you, right? Just compute the syndrome. So if Y is 1, 1, 1, syndrome is 0, 1, you see 0, 1 is the second, which one? The third one. So that means 0, 1, 0, 0, you need to subtract from the bits, right? So you will get the actual X. Right? This is how you do the syndrome decoding, right? Any question with syndrome decoding? So I talked about sphere decoding, I talked about coset decoding, and now third thing is syndrome decoding, right? So now I'm going to construct the first code which was discovered by Richard W. Hamming, the first error correcting code which can correct single bit flip. The idea was really very simple. He was trying to arrange the bits in such a manner so that he can correct single bit flip. Okay, without worrying about syndrome or anything, any of these definitions were not there. He was just trying to arrange the stuff, vectors, so that you can correct single bit flip. Hamming code and its variations are quite useful for fault tolerant memories in your VLSI hardware. Variety of places they have applications, right? Because if Hamming code is not there, you will find that the fault tolerance in the hardware is not possible. It is all dependent on different variations of Hamming code. Okay, where so now actually what happens depending on the scenario or the channel under consideration or the physical scenario where you are storing the bits or transmitting the bits, the kind of errors are different. Okay, in some cases you can have only single bit flip. In some cases you will have multiple bit flips, right? So the idea is that as an engineer, so whenever whatever is the requirement, based on that you choose that codec to actually take care of your stuff. So let me talk about the Hamming code now. Okay, here is something. Again, I am focusing on binary. Everything can be generalized to field with q number of elements, but I am not worrying about it. At least you should understand the big core concept. So now I have to construct a binary Hamming code. So what I need to do, I am going to give you a parity check matrix, a construction of parity check matrix, and then automatically everything will be done, right? So what I need to do, if I take m is equal to 2, right? So m is equal to 2, how many vectors are there of length 2? 4. 0, 0, 0, 1, 1, 0, 1, 1. Right? I am putting these vectors as a column of the parity check matrix with this condition that no two columns are multiples of each other. No two columns are multiples of each other. So 0, 0 you cannot put because that will be a dependent thing, right? Okay. So you start with non-zero, 0, 1 I can put. Once I put 0, 1, I can also put 1, 0 because 1, 0 and 0, 1 are never multiples of each other. Then I can put 1, 1 as well, right? Because 1, 1 and 0, 1 is not multiples of each other. 1, 1 and 1, 0 is not multiple of each other. Although 0, 1 plus 1, 0 is 1, 1, but that's okay. I'm not worrying about that. I'm only worrying about that two columns should not be multiples of each other over binary field. Two columns should be linearly independent. Okay. Okay. That is the condition. So there will be only 3 vectors, correct? If I ask the same thing for length 3, how many vectors will be there? All 7. 1, 2, 3, 4, all 7, right? Total 8 vectors are possible of length 3, right? One vector will be all 0 vector. That is not required, right? So only here left is 7 vectors, right? So this is how. So essentially, in the case of binary, it is very easy. The Hamming code parity check matrix has all non-zero tuples, all non-zero m tuples, right? If agar hum length m le le, all non-zero m tuples, so they are part of the parity check matrix. Now this parity check matrix, so will give us a code C, which is the all those vectors in Z23 such that Hx transpose is equal to 0, right? If this is the parity check matrix, it will give us a code of length 2 raised power m minus 1. Why 2 raised power m minus 1? Because if you take length m, how many non-zero columns are possible? 2 raised power m minus 1, right? Dimension will be 2 raised power m minus 1 minus m. So this is something which requires a little bit of proof. Why the dimension of this space is this much, right? And the distance turns out to be 3. I can give you an idea why the distance is 3. Because of that condition that no two columns are multiples of each other, distance turns out to be 3. Okay, so this is a t time problem, right? Exam may be puche maansoon mein na. So why there are, if the distance is 3, why there are, we can, if the basically no two columns are multiples of each other, the distance turns out to be 3. Anyway, so let me show you a couple of things. Number 1, can you make h in case of 3 from h in case of 2? See, can you build from the lower to the top? So for m is equal to 2, using m is equal to 2, can I make m is equal to 3 matrix? Can I do that? Actually, if you do little bit of arrangements, you see, here you can draw a line, here you can draw a line. You will see that this is the parity check matrix of the m is equal to 2 case. This is the parity check matrix of m is equal to 2 case with one extra column of all 1, and then top is 1 and 0, right? So that kind of arrangement you can do actually. So what I am saying that m is equal to 3 case can be built from m is equal to 2, m is equal to 4 can be built from m is equal to 3, and so on. So there is a way to develop it, the parity check matrix. There is a relationship which you can build, right? So you can build all the parity check matrix from m is equal to 2. That is something easy exercise for you. Now, decoding part. Suppose x is sent from the C, which is the Hamming code, and Y is received. And E is the error vector. E is equal to E1, E2, E3, En. So what I can do actually, what is syndrome of Y? Syndrome of Y is syndrome of X plus E, because Y is X plus E. X was the vector which was sent, E is the error vector that is added. Right, so if E is 1, 0, 0 means first and second bits are flipped, and last bit is as it is, right? If there are three, length is 3, right? So essentially, syndrome of Y is syndrome of X plus E. This I can open, this is nothing but syndrome of X plus syndrome of E. Syndrome of X is HX transpose plus HE transpose. Now HX transpose is what? 0, because X belongs to C. So this portion is 0. You are left with HE transpose. So syndrome of Y is HE transpose. This is a simple formula, right? Now, if parity check matrix I can write down as columns. First column H1, second column H2, and so on, last column Hn. If I can write down as a columns, and suppose error vector E is 0, 0, 0, and suppose at 3 places A, B, C, it is 1, otherwise it is 0. Suppose error vector is like this. So HE transpose, syndrome of Y is HE transpose is nothing but sum of the columns where the error occurred, HA plus HB plus SC. Beautiful observation actually, right? Just computing the sum. Syndrome is HY transpose, HE transpose here in this case, right? So E is error vector. At some places it is 1, some places it is 0. Wherever it is 1, those entries will contribute here in the sum, right? So essentially it is saying that just take the column sum of those columns where the error occurred. This is nothing but the syndrome. In case of Hamming code, this turns out to be very simple, because here I am assuming that error is 3 bits are corrupted. In case of Hamming code, because it can correct only single bit flip, error vector will be what? E is equal to 1 at some position out of n positions. All other places are 0. So 1 at some position, and other places it is 0. So when we compute syndrome, in case of Hamming code, it will give you the column vector in the parity check matrix. Just look at which column vector it is. Right. So if it is third column vector, just decoding is simply flip the third bit. If it is the fourth column vector, just flip the fourth bit. If it is the first column, you just flip the first bit. That is how so easy in Hamming code, right? No, then the things are different. I'm just talking about binary right now. Okay. So because then even the whole thing will be also different a little bit, but a little bit more complicated. That's all. But binary case is obviously simple. That's why Hamming code is very simple thing, right? So if you use Hamming code, use the parity check matrix of the Hamming code. You send a vector X from Hamming code, Y is received, compute the syndrome, it will be a column vector. Look at which column is in the parity check matrix, whatever is the position, just flip that bit in the X, in the Y, actually you will get X. This is a very simple decoding. So decoding is very easy actually. You don't have to maintain all those tables, this and that, anything, right? Okay, so this is something really straightforward for Hamming code, right? For binary Hamming code is very easy. For non-binary, a little bit more complicated. That's all. I mean, what else? Okay. By the way, decoding in general is a very, very difficult problem. It's a NP complete kind of thing. So, the whole branch in coding theory, which is totally devoted to decoding, art of decoding. There are different ways people have developed methods. There is another popular method known as list decoding, which is by Venkat Guruswamy from MIT actually when he did his PhD. And there are many other people who have done different kind of things. List decoding is very popular, right? Then depending upon the structure of the code, sometimes decoding can be simplified. The way you construct the code and so on, the decoding will become simpler, of course. So general decoding schemes I told you, in general, based on vector space properties. But if you use some properties of the code, the way they are constructed, actually, they are very, very popular. Now, another thing, Hamming code was generalized to what is known as BCH code. Bose Chaudhary Huffington code. So Bose is of course R.C. Bose from Calcutta, who was in US, and Chaudhary was his student. And independently, the third person, so they discovered what is known as BCH code. BCH code is known as mother of all code because it's very engineer friendly. If so, I show you brief idea how taking the parity check matrix of the Hamming code and then modifying it, add another parity check matrix on the top of it, it can correct 2-bit flip. If you add it bit further, you can get correct 3-bit flip. So Hamming code idea can be generalized to whatever errors you want to correct, you can actually do it easily. Okay, so that's why the BCH code is very, very important. Okay, both Chaudhary Huffington code, BCH codes are mother of all code. And it turns out that whenever you are solving, actually whenever you are decoding BCH code, it leads to bunch of system of equations over finite fields, and solution of those equations were given by your famous friend Ramanujan in 1912. Okay, so when he was quite young. So in Indian journal, he published that result. So basically, you see the connection between BCH code and the equations that the solution given by Ramanujan. It's a really interesting thing, right? So decoding leads to bunch of equations over finite field, and solving equations over finite field is a very, very difficult problem. Okay, I think you must have seen some flavor in discrete math. Even the equation ax square plus bx plus c is equal to 0 and abc over z2 is a bit non-trivial thing, right? Or even z3, z4. Still you are trying to find solutions, right? It's a very difficult thing to solve these equations over finite structures, right? So, but anyway, so there's a lot of things to do actually. So if you want to, many times if you find a beautiful solution to certain equations, it may lead to efficient decoding algorithm for certain codes, right? So that depends on which kind of code you are looking at and what you are doing. Okay, so I just start the another important thing, what is known as cyclic code. What is cyclic code? First of all, it is linear code, means it's a subspace. Second, it has this property, take a vector, do the cyclic shift, it is again in the set itself. Okay, it's again a code word. So basically, if C0, C1, Cn minus 1 is in C, it's cyclic shift. You just Cn minus 1 here and Cn minus 2 here, just shift is also in C. It's a beautiful property. And this cyclicity actually saves a lot of space and the complexity. So for example, if you look at this code, this is a cyclic code, right? Take this vector, shift it, you are here again. Take this 101, you shift it 110, you are here. 110, you shift, you get this. Shift here 101, you get this, right? Each vector, first of all, it is linear. That's a beautiful thing. And second thing, cyclic shift is again in the set. So such kind of code is known as cyclic code. बाकी बातें इसके बारे में we'll talk about in the next class, but I think some basic idea. There are different kind of construction of cyclic codes. It turns out that almost all good codes are cyclic. Another interesting property. Okay, and some of the popular codes, Reed-Muller code, Reed-Solomon code. You will see that the Reed-Solomon code is basically used quite a lot in storage. Your hard disk, your many other devices, they use some variation of Reed-Solomon code. There is a book in the library, Reed-Solomon code and their applications by Vijay Bhargav. You can look at it, the different kind of applications that have been developed by Reed-Solomon code, right? So it's a very, very popular code. Okay, so we'll talk about some idea about the cyclic code, and then I'll give you an idea of BCH code. Then we are, I think, ready for you to describe the DNA storage channel, right? So what kind of problems are there now? This is the basic thing which I covered. Okay. Any question at this point? How many of you have filled the form? All of you? Right? Some of you have not filled the form yet? Done? No, actually, I am thinking in case of project, we will be meeting at least each team once in a week so that you are not lost. Otherwise, see, there's a huge literature. You will be lost very easily, right? And rather than you going into the wrong direction, even if you meet for only 15 minutes, that is enough for you to harm. No, but at least the basic idea you want to know, whether you want to do the review writing or you want to develop a simulator, a coding, that I think that much is should be known. Yeah, of course. I mean, we can see if you think that it is not coming up, you can always change it. Right. There is no limit. It's entirely जिसकी जितनी श्रद्धा प्रोजेक्ट के बारे में मेरा तो सिंपल यही फॉर्मूला रहता है जिसकी जितनी श्रद्धा the amount of efforts they want to give accordingly there will be output, right? Okay, so I think by evening, I mean yesterday evening there were only 4 or 5 entries. I'm not sure what happened in the night. I will just check it. Okay, so I think by from next week or something we will try to meet each team 15 minutes every week so that you're in the right path, right? You not, I want individual attention. Otherwise, what happened last time, people are doing random things which is of no use, you go on Google, search something, junk papers, attach it and say it's all done, right? Nothing is done, right? So, because you see it's a major component, 50% is more about the projects, right? So I think it's good that we meet at least once in a week, right? That's all. 15 minutes, that's all. You'll fix a time, right? Okay, thank you.